Okay, this is, I think, section 2.3 for our connection design. This is the design per 358, and I'm actually taking all the design steps from the 358 draft ballot version and going through each of the steps in detail for just the language at this time, but I'll go into actually the design of each step later for a couple more presentations. So we'll go to the beam link column combinations analysis and actually design requirements per the 358. So this is the design of what's in the 358 document. These numbers here are actually ballot numbers for people if they have any questions, so they can refer to which line in the document. So first of all, general, as you can see, is spelled out as a partially restrained connection. So we're telling people up front, ours is a PR connection. Yeah. Okay. So when they do the analysis, you need to make sure you include the behavior of the connection, and we tell them how to model that later. Down here is the connection is based on capacity design approach. I'll go into that capacity design a little bit. Basically, you have a link element. You consider that design everything around it to be stronger, like we said before. Make sure you have a fuse, and then design everything stronger to be your fuse. So that's the capacity.
The fuse, that's the fuse. So we mean
that's the
link.
That's the link. Yeah.
The fuse in the sand.
Yeah.
And link.
Okay. So and then the connection response remains elastic under factor low combinations. Factor low combination, that's our of the low combinations, so that we call it factor low combination. So no, connection remain elastic, so we do not yield under those stuff. So that's why I go through some of the backgrounds first, and when you read this document now, you understand a little bit more what we mean by the different terms. Our system could be a SMF or IMF. So we are qualified. So when I show you that we qualify for 0.04 radians, that's more than the 0.02. Yeah. So we qualify. If you qualify for SMF, then you qualify for the IMF as well. So
we rarely make the IMF.
We don't really do too many IMFs because if you do IMF, you might as well go to the SMF and get better improvement. There's not much cost saving. There are sometimes. The couple items I point out yesterday was mostly strong column, weak beam. Yeah. That if you want to do that, you might want to go with the IMF. That's traditional connection. But ours, we reduced it so much here that strong column, weak beam check is not really a issue at all. So why not go with the SMF? Because that's one of the advantages with the IMF is because you don't have to meet that. Yeah. Because that's not really a concern. So it's not. Yeah. So we might as well go with the SMF. So 1.3 is qualification limits. What are we qualified for? So the beam, we could do a Y flange, the W shapes, or we could actually build up our I shapes. Okay, so we left it open as in just from the steel manual, or if we need to, we could build up whatever shapes we want. However, it is the limit to a maximum of W16 for row shapes, and the maximum depth of W16 for build-up shapes. And when I go into that a little bit later to tell you what's the W16, there is actually a lot of range of W16. It's typically W16 by some number, and that number is pounds per linear foot. So how much each foot weighs. So 16 by 50, 16 by 45, 16 by 30. There is a 16. And there's a weight associated. The depth, though, the 16 is somewhat of a nominal number. So it could be 16.1, could 16.4, 16.8. That depth it varies as well. So but what we're saying is do not exceed the maximum depth in the W16 shape range. So we're giving us the benefit of the doubt that if we want to go with 16.8 or whatever, we could still do that. There are no limitations on the beam width to thickness ratio beyond those listed in the specification. The reference here, when it says specification, is referring to the 360. 360 is the specification. So that's what the reference here is. Typically, how they write it is the specification. So no thickness ratio between the two. And I'll show you later what's the difference between the AIS 341 and the 360. The ratios are typically a little bit more stringent in the 341 versus the 360. So we're going with a less stringent one because the reason is we're not yielding the beam, we're not deforming the beam. So like I show you, we're not buckling the beam flanges. So the ratios, or for that ratio, is really trying to limit buckling of the flanges. So we're not buckling it. We're going to go with the ratio in the 360. So that's one check. No requirements of stability bracing of the beams or joints beyond those in the specification. Okay, so we're not bracing, lateral bracing the beams and the joints. So the 341 spells out lateral bracing at the beams at the connection, along the beam, and also at where the change of flexion point, or where you have a point load coming down. On ours, we say there's no requirement beyond that of the specifications, and the reason is we're taking care of all those, making sure that we don't form a hinge in the beam. Let me see. The next one is the protected zone. I'll show you a figure later. Protected zone means we don't want the contractor or anybody to do any work to that zone to damage the location. Yeah. So like for RBS, they typically no welding, no grinding of that area, because if you put a shot pin or screw on it, then you create a notch toughness at the location. So when you do it, and potentially you can break easy. So we don't want them to touch that. So and we have that we have that highlighted later on. So our protected zone is anywhere in the top. I mean, basically, it's not really the top. I say, is the top and bottom link. Okay, top and bottom link, and the shear tap region, and is where it's in contact with the flange. So if we're away from the flange, it's okay. We're just saying when we're in contact with the flange, then that's protected. Contact with the flange. So that's our protected zone. And here we spell out there's a shear plate, horizontal slots in the top and bottom, which I showed you guys before. Standard hole in the middle. Terminology is, this is called the link stem. This is the flange. So when we're doing the design later, we know which one is which, and that's the reduced region in the link. So these are some of the terminologies. What it is: the BRP bolt is the one that's restraining it, and there's a BRP plate on top that's restraining the buckling restraint plate, restraining it from buckling. And then we also have the link and also a spacer plate, which we saw yesterday. So these were actually all in the code, and we show people what the connection looks like. Furthermore, in the link itself, now this is a blow up of what that is. We have definitions on how to basically, all geometries, how to control our link. So this is the W column side. This column size, and then this is the beam side, is how wide this side and how wide this side. Typically right now we trying to keep the two the same, because fabrication is easier, just one cut instead of having to do different widths. But the column side, this is the critical yield, W yield parameter we keep saying, and then what's the yield length, what's the column side. Our equations I'll show you later. Each step would calculate this number and how to determine the number. For the welding, we are still allowing a fillet weld, but with a more stringent requirement compared to what we actually have tested, and also a CJP. But all the ones that we are fabricating is our CJP welds. So these are the welds. And T stem, that's the thickness of the stem. That's always 1/2 inch for our report. T flange, this is always 7/8 or 0.875 inch for that. Because we're fabricating it, we don't want to change too many thicknesses of steel, because when you stock it, You want to limit it to certain shapes, and so when you buy it, you buy a lot of them, and you keep using it, so it's a little cheaper instead of having to change it. And our guys in the shop, you don't want to confuse them either. They could use it, simplify it as much as possible, so they don't make mistakes in the shop.
But when we provide the design, we dimension on of the.
Yes, we give dimension on all of them. So.
They get this, they can.
Yeah, exactly. So the fabricators, when they see this we don't need to give it to the engineer, or they might even give it to us, but to fabricate it. So these are some diameters. So the G is this one, the flange width, and then the S is the spacing of the bolts. So these are some of the parameters. There's a link flange, link stem. So these are some of the numbers, and when I get into it, S is basically the edge distance to the column SC. SB is the edge distance to the beam, and this the S of the stems between spacing. Column limitations, we just covered the beam and now the column. Again, column could be rolled shapes, Y-flange shapes, or build up, same as the beam. The beam shall be connected to the flange of the column. That's the one we're saying no corner connections, no bilateral. So we actually spell out that's where the requirement is in this here. Column depth is limited to a maximum of W18, or maximum depth permitted for W18 shapes if you build it up. So same thing. That's where the requirements are. And again, these are because that's how big we test it. If we tested bigger sections in the future, then we could come back and modify this one to say whatever we tested. Okay, no weight limit for the beam. We said that before. No additional requirement for flange thickness other than what's in the specification. Again, no. The width to thickness ratio, keep hammering it. Nothing beyond that of the specification. Okay. Lateral bracing of the column shall be provided in accordance with AIC seismic. I'll come into this one a little bit later, and that's part of it. We do have to brace the column top as a minimum when we're doing it for stability. So not just the whole frame is not braced. There's the exception. If the MN the flexural strength outside the panel zone is limited to the SX FY, then we provide bracing at the top flange of the beam only, near the top flange level, which is kind of the top, if we meet this requirement. Okay. If not, then we need to provide bracing at both the top of the beam and the bottom of the beam. So this requirement is the big one we have to check. And for design, typically this is ZX instead of SX, and the difference between the two is about 10 to 15%.
The MP.
Yeah, the MP is typically that. So that's the exception. Another one, bolting limitations. Okay, all bolting shall conform to 358 Chapter 4. They have requirements for bolting. We're applying some of them to some exceptions to our connection. The following connections shall be made with 8325 installed in snug tight condition. Okay, snug tight, I'll go into that a little bit when we're talking about bolting, but it's this is the connection we're talking about for snug tight bolts. This going into the column, these 4 bolts are snug tight. Okay, and then the buckling restraint plate bolts, these 2 bolts they're bolting in, they're also snug tight. And then the shear tap bolts, or the beam to the column shear tap, those bolts are snug tight. Right. These ones here to the beam, they need to be pre-tension. Pre-tension means there's a lot of requirement with the pre-tension. Snug tight versus pre-tension, essentially when you again look at the stress strain curve, snug tight is really in the lower region. Pre-tension, you actually tension almost all the way up to past yield and ultimate. So it takes a little bit more effort to get to a pre-tension bolt compared to snug tight. And sometimes the equipment is required to get to a pre-tension level. Beam to column relationships, like I say, the panel zone shall conform to requirements of the specification. And the requirements and specification, they have a fee factor of 0.9 in there. AIC 341 is actually fee of 1. So we're actually more conservative going with this one. Okay. As well as the column beam connection. So we have a strong column weak beam. So instead of strong column weak beam, we don't have a weak beam. We want to make sure we meet the strong column weak link. Okay. So this is the requirement for that strong column weak link. So that would be under for 1.4. 1.5 continuity plates or stiffener plates. So essentially require where it is in accordance with the specification. One thing about it is the continuity plates shall be permitted to be welded to the column flange and column wet with fillet welds. Okay, that's a critical one. Typically, a lot of the fully restrained connections where they test the continuity plates, they actually require a CJP weld to the flange for these stiffener plates. So CJP weld means a lot more expensive, inspections required. We allow it to be fillet welds. We test it to be fillet welds, we allow it to be fillet welds. So that's cost savings a little bit more compared to other connections. Okay, here's the T-stub to the link stem limitations. And again, this is the T to that. Those are the two welds. This one could be a fillet weld on both sides or a CJP weld. And that's what's there in 1.6. 1.7 fabrication. Typically, we have a limitation on how smooth this is. The reason is we saw some testing. If they cut it, it would be very rough and stress concentration. So we want to make it smooth, and we give a smoothness requirement on the fabrication. Yeah. Okay. And it's 250 microns, or actually 6.5 microns, micro inches. Okay. Where is smooth? And also, because we're counting on how much neck down the width, we're giving it a pretty tight tolerance, cutting tolerance. Okay. It's plus or minus 1/16. So when we want, say, we engineers specify, okay, I want a 3-inch. Okay, 3-inch. They don't always cut you 3 inches. Okay, there is a plus or minus tolerance that they give you, as long as they meet 3-inch plus 1/16.
For each direction
from the cut line. So yeah, plus minus. I think it is direction from the cut line. So we get plus or minus 1/16. So that we have all that on the drawing, in the production drawing. So call out, but I just wanted to point out when you look at the different sections, that's what we mean by that. So 1.8 connection detailing. I'll show the beam cope a little bit later, and then I'll show you what the beam cope is. And then the T-link. Stem thickness shall be 0.5 inches. That's where the 0.5 inches is coming from. And also material, it could be A572 grade 50, and that's what it is right now on the AIC. The code report, we're only limiting to this, but AIC, we're saying we could also cut it from beam or columns that are grade 50. So imagine, instead of having to weld it where we have those beam and column W shapes already, why don't we just cut it from there and don't have to weld it, right? We give us a reason out so we could actually do that. We did not test it that way, but saving us the weld top and bottom, since they roll it out that way anyway, this should be cheaper. But that we gave it there, we have not looked into it. The reason we're not doing it is because typically when you do those curves are pretty big. The K area, the bigger you go, the bigger curve area. And when we put in the bolt and the washer, that was interrupting the bolt and the washer. So we can those are built-in K areas. We cannot touch anything. So that's why we allow it. We still allow it there if there's a big job that fits. But right now we're just limiting it to what we're just building it from plates right now. Shear plate bolt connection. Pre-qualifies shear plate only for one single column of 3 bolts as shown. So we only qualify for 3 bolts. Okay, center bolt, the other bolt. This is called coping of the beam. Okay, you could go straight down, go this way. You could go straight down, go that way, or straight cut. Okay, as long as we clear between this and the shear tab for when you tilt it up. I have a picture during the design what we mean by rotation. So at least you have a gap, so you don't hit it. You don't hit the other parts when you're doing that. Then that's okay. Shear tab connection to the column should be double-sided fillet, PJP or CJP. This is the column, and there's a shear tab where the beam connect to. That connection, it could be anything. Typically, we're done with fillet welds. Fillet welds the cheapest, followed by PJP, then CJP. So that's the cost of each. Bolt holes. I think I'm done with the geometry, but this is oversized or vertical slot holes are permitted in the column flanges, and I'll show you some of those later. And I talked about it before, where we have the W shapes that varies by it could be up to a quarter inch. To take up the tolerance, we actually have slots in the column to take that up. So the top and bottom holes in the shear plate again should be slotted. So the top and bottom those shear the shear plate, we have slotted holes that needs to accommodate 0.07 radians. The center hole again is a standard hole. We show that on the beginning picture, but this is where it is in the section. Again, this is quick. Buckling restraint plate shall be 0.875 inch thick. No other thickness that we just call 0.875 thickness. Okay, and the restraint, the bolts here, needs to be minimum of 0.625, a maximum of 0.75. We don't want it to be too big and tighten it, because remember, when you compress on it, the plate could expand and contract. If you tighten it too much, we can't let it expand. So that's somewhat of the requirement. Shims, we typically don't need it. Shims are if you're connecting this into the column, and this, let's say it's not straight, it's a curve, and they allow you to shim it with some shims, so you could bearing contact, kind of washer somewhat. So that's shims. We're allowed to use it, but we most likely we don't need it. And columns, they're not part of our lateral force resisting system, so columns are not part of the frame. We have some requirement for them to design as well. When we come to looking at the top, this is the buckling restraint plate. These 2 holes cannot be more than 5.5 inches. Okay. And also, there is a clearance, like I told you before, that's the 1/8 clearance that we're looking for them to expand. Design procedure. So that's finally, after all those are all the how we put it lays out. Typically the material qualification, all the restrictions on beam and column, and all the geometries on the connection. Then you come into the design procedure. Like I say, we're going to modify it slightly compared to this when we do it ourselves, because this one you're going to do a lot of iterations if you follow this procedure on the top. What they say is, okay, choose a trial beam and column subjected to the qualification limits, assuming a fully restrained beam column connection. Why is that? If they have not used our connection, they don't have a K value to go with yet in the beginning. So we're just telling them, okay, just do it like you always been doing, just without having to consider that. But in order to capture, we know our stiffness is a little bit less than the fully restrained. We say, okay, multiply by your drift to get to the PR connection. Okay, so to approximate our connection, we asking the engineer design it like you typically do, but for your drift check, because we know it's a little bit more flexible, multiply by that number by 1.2. Okay, then when you have something, go on to the other steps. So for us, the Excel spreadsheet, if we choose a link, we know what that stiffness is. So instead of going to this step and iterate through next time, if the drift thing is very sensitive. If they put it in 1.2 and then they calculate everything else, and then they have to check drift again, assuming an actual connection, right?
Yeah.
Then what if that one doesn't work? Then they have to go back and choose another connection already. So what we're doing is we're actually jumping to the second step, eliminating this step, jumping to the not this second, jumping to the actual connection to evaluate drift. So I'll show you how we're modifying a little bit. But this one, for people that have not used it, then we're saying go with this one for now because you have not used it. But if they design a couple of times, they realize, why would I have to do this one if I know what my stiffness is? Why don't I just put it in the beginning? So, okay, so that's step one. Step two, like I said, check beam strength and deflection, assuming a beam is simply supported, okay, between the shear tab. And that's to check your vertical beam strength under that. So service load. And this out over 360 could be adjusted based on the stiffness needed. So other values may be acceptable. So we're saying that I actually put in the spreadsheet. I saw some governing. I'm going to say, well, I'll go with 300 or 240. So just need to let them know if you want to do that and put that as something on the calculations if you do assume that. Okay, step three. I tell you how to calculate this area. So first of all is the P. P is M over D. Okay, so once you have a P, then you divide it by the Fy to get your area. Okay, so these are all the terms are defining area as the estimated U area. So this is relatively easy. P divided by Fy, you get A. A is what's required. Step 4 is to determine the column side, the beam side, column side, beam side, and I'll go do this in a little more detail. So step 5 is now to actually calculate what is your yield width. Yeah, so that's how you calculate. Once you know the area, the thickness is always the same. Yeah, so then you could calculate the width. So that's the strength. This step 6 is actually limiting the yield length to try to calculate a length. So your string is equal to or less than 0.0585. And that's one assumption that we made is 0.085 at 5 right radians. So essentially, just to summarize, we're gonna calculate the flange width from this step. We're gonna calculate the column side from this step. We're gonna calculate the yield from this step. We're gonna calculate Ly from step 6. Okay, so we know all these parameters already after these steps. And also because we set this one equal to that, we also know that one for our calculation purpose. So what we're looking for is actually how do we determine these for the geometry, and as well as the thickness of the flange. So compute the expected. After you know the area, you want to compute the expected yield and maximum probable tensile strength. This is the maximum yield strength that our link could deliver, maximum ultimate. Okay, this is the yield, this is the ultimate. RT FU, we're using an FU value instead of Fy value. So 50, 65. So RT RY, we're using 1.2, and this is 1.1 typically. That those are, and I'll show you what these come into play later. So Now after you determine that, then you size the other side of the bolts and all that stuff for that term to design it for the PR link. So we're designing everything for this higher low. So all the bolts that we're sizing, make sure we could size the bolts to be greater than that. So this is what we're calling the fuse capacity, I guess. And you're designing everything else to be greater than that fuse. So that's what we're doing. Okay, so essentially after that, from this step, you could determine the bolt diameter. After the bolt diameter, then you could determine how many bolts you need. Then you could determine the L beam size. So this step would determine this. Okay, so you have all the geometries after step 8 to design our link. Now is the flange thickness. Right, we know the stem, everything now how thick. We say we provided all the same thickness, but for this is for the engineer to check. They could provide whatever they want. So, but we also need to check it, make sure that it works. So this is to check the T-flange thickness. Okay, so we check it for preventing from prying, and then we always assume 4 bolt configuration. And then check flange thickness for shear. Now after that, you design the connection. So I say before we allow 2 types, the CJP and then the double-sided fillet. The double-sided fillet, the CJP, you don't have anything else to do. There's no calculation required if you just call out that one. Now I'll show you what that actually strength would be. But for the double-sided fillet, previously we're designing the double-sided fillet for the yielding. Okay. Now the beef up version is we're designing the double-sided fillet for this area instead of this area. So it's a lot bigger. So to prevent it, so you would need a bigger well to get to this area yield and this area yield. So that's why we still allow it in this one, but we make it a little bit stronger, utilizing the column side instead of the yield area when they're sizing that force. Okay, step 10, buckling with shrink plates. I told you, we just pick it. We only have one size, and then the 2 bolt sizes, so that's not much to do. Step 11 is to determine the property K1, K2, K3. I'll show you guys what those are, and it's actually in the report. And those are the 3 linear springs to approximate it, and the effective spring, what the MY, MPR, delta, delta Y. All these are calculations they could plug in to get to the curve, the connection curve. Okay. Think about it. They would have to go through all those steps to figure out what this are, what that is, to get to this step. If we're selling the link, and if we know all the geometry already, all we're doing is necking down, then all you have to specify is L, M, or H. Then you could calculate this connection without having to go into designing the frame. That's independent. So you could do this step anytime you want. And we know what it is. So that's why you could eliminate that estimate step from the top. You know the geometry, you could estimate all those, you could calculate all these properties already beforehand. So you don't have to jump to that step. And I'll show you one tomorrow when we're doing the step analysis. I'll go through what's actually in this one and go straight into what we're doing and see what the advantage of this one is. Okay, design procedure. When after they put in this, this curve, then they have to check the drift based on that curve. So now that's the actual stiffness that they're doing to check the frame. Okay, if the connection and check the MU and MY, if the drift doesn't check, or we're saying adjust the connection stiffness or number of connections that needed to comply. What we're just trying to say is, if your drift doesn't check, adjust your value a little bit more, try another one or try another column to make it work. That's the iteration we're saying. This is the iteration, iterate through. If the first try doesn't work, try something else. Try something else, it doesn't work, okay? That's why I say instead of having to do so many trials, we're trying to simplify and cut down the number of trials we're doing, or modify steps. Okay. That's step 11.1. So now, no, they calculate that. So basically, check it after you put in the actual connection. And now, knowing the beam size, after you drift the check, so you pretty much have a final beam size and the column size and the link size, right? So knowing those two, our next step is to check the beam connection to the column and the shear tap connection. So here are the steps to generate the loads to check those connections. So we want the MP divided by LH. Here's the shear tap. This is the capacity. This is the maximum capacity, assuming all the links yield that you're generating as a shear capacity. And in addition, we want to add in the gravity as well. So this one, I'll show you what we mean by that later on. What do you mean by the VU? And the step by step, I should show a diagram what that means and why do we use the 2MP over LH. And if you use, and also if you have frames that have a connection on one side only, then it's not 2, it's just 1 MP. So that's what it is. And I'll go over that a little bit when I actually go into the design step by step. So 13, verify beam and column sizes in step 1. So they assume a beam and a column and design it for the rigid connection. But now knowing the link, we want them to design the beam and column. So actually, when we yield a link, this beam and column is still okay. So because yielding a link is a lot higher force than just the seismic, the earthquake force. So that's where capacity comes in. We want the beam and column to be good when we develop the link. Okay, when we size this link, we're just based on the elastic portion. Now we want them to go back when they size the beam and column, and then also previously they sized the beam and column just based on the link elastic. So now the next step is we want you to size the column and then the beam, assuming yield, assuming the worst condition, assuming the ultimate, which is at top of the curve, for that force. Instead of elastic force, we want you to check it at the ultimate force. That's why this is an extra step check for that force. Okay, so then check the beam, check the column for those 2 steps. Check the beam column relationship, strong column, weak link. That always, we say that's always checked. We just refer back to that. Now beam web to column flange connection. We want to, that's the connection of the 3 of the shear tap. Again, this is step 15, and on my follow-up presentation I'll show you what this step 15 is and what it is when you're checking it. So first of all, we have to check for combined shear and axial, and then the shear is 3 bolts are taking shear. When you're doing the axial, you only have 1 bolt because the top and bottom are slotted. So when you're pulling on it, the slot holes don't take any axial. Only the middle, only the center bolt takes it. So when you check it, you only assume the center bolt. And also when you're doing the shear tap, you also check the a moment that's due to some sort of eccentricity. So you have to check that as well. So here is the VU divided by the 3 bolts. The PU taking all of them by 1 bolt. So the center bolt, that's how much the center bolt have to be resisting. Okay, so we size that, and then to size the center bolt, we say go to the specifications. So that's now sizing the center bolt for that. So with that, you have the bolt from the center. Now the top and bottom slots, we want to make sure you have this slot, so the connection can rotate, and then how long the slot length, the top and bottom. Here's the slot equation to do it. Now after that, you want to check your shear tap for tension and yield and tension and shear. Okay, and the welding of the shear tap, and then the beam web tension. All this. These are the steps. Now I'll cover one later, but these are where we are in the design procedure. Step 16, check the panel zone for the strength. This is the one that I tell you. It's independent of the analysis.
Yeah.
As long as you know what this maximum PR low is,
Yeah.
you just pick a column and then you check the panel zone, see if it's good or no good. That's one thing that you should be checking first on your list, is check the panel zone. If it works, then that column's okay. If not, then you have to go with a different column.
Yeah.
The beam is a different story. Okay. Now you check your column web for the concentrated forces. I'll go into all the different concentrated forces later. Step 18 is check your minimum flange thickness. We have minimum flange thickness, then that's at the top and at the bottom of that. If your flange is no good, or if the web is no good, you have to stiffen it, then here's how to calculate the stiffener and what force to calculate the stiffener. As a minimum, the thickness of the stiffener should be 1/4 of an inch. Okay. And that's it for the design procedure. A little bit, no, 19 steps, not too bad. And I'll go, like I said, I'll go into very detail in terms of what's resisting in the moment, what's resisting axial, and what's resisting the shear, and how we calculate the capacity, and how we calculate the bolt size, the weld size, later on in another slide. This is just to introduce you to our design procedure, what's in the code and what's in the 358 when you see it next time. For our beam and column stock sizes, I show you before, we have 4 beams, 4 columns and 2 beams. Here is its actual geometry drawing for our links, for our L, M, and H. All these are just by necking down this. Okay. And the thickness is always 0.5 inches. So yeah, thickness is always 1/2 inch. So combinations, this is actually panel zone is governing. Okay, like I said, check your panel zone first. For the column, we have 4 columns. If I put in a light link, my panel zone DCR is 1.03. If put in a medium link, my panel zone DCR is higher. H link is higher. What that means is, on my light column, I cannot use a medium link or a heavy link. I only are able to use the light link to combine with our smallest column. So the same thing for the W12, I could only use a light link with that column, because if I use a heavier link, the panel zone is going to govern and it's no good. So I could only, that's why I say check the column panel zone, then you know if the column's okay with that length or not. So here is the possibility of combination for the catalog stock sizes. When we're dealing with W10, only light link, W12 only light link. For the heavy one, actually we are 16 by 15, not this one, is L, M, or H is okay. So you combine with anything else. So that's what we mean for, there's L, M, and L. On all of them, we have to call out what link size we're going to use with that beam or column.
What is this wing?
This wing is actually before. It's an old one. It's an old one. I don't know what it is. It's an old. Previously they tested.
So we have to mark on the link.
Yeah, they have it in production that I think they're color coding it to be different size link. So again, for low combinations, different combinations for our custom, we could combine with only the L link. So we combine the beam. Now this one is beam and column. Then you could combine with the L. But for the 14, the L and M. For the 16, we could do LMH. So that's why we get 13 combinations for custom stock. So that's this is the engineer's design. We help them maybe. So, but right now we're still with W16, 18, and 3.5. So those are limits. Okay, review. Since strong frame has a PR connection, additional requirements is required, like you guys seen before. PR connection modeling is required. Frame drift needs to be checked for the PR connection. We incorporate capacity design approach in the frame and connection design. So basically, The fuse is a link, is a U-link. You design for that first, and then you design everything to be greater than that capacity. Once the ultimate capacity link is determined, all elements of the connection member, the beam and column are designed to have greater capacity than the link. Since the beam and column are designed to be essentially elastic, that B over T ratio needs to only meet the 360. I mentioned that. Other than drift, beam column panels don't govern many frame design. Check this variable first. Okay, that's it. Good timing.
Long time.
Yeah.
That's what's up to the guys.